So in this video, I'm going to take everything we've learned about quantization and also dequantization. We briefly covered how to dequantize a value and translate it all into code. First, we're going to use PyTorch to quantize, to represent our tensor that we want to quantize. And I'm going to replicate this example, but with real numbers. And so I'm going to choose to have a tensor, which is PyTorch's way of representing an array. Particularly for a neural network, and I'm going to represent them by the numbers -500, 100, and 300. I know given the range of numbers here it's not drawn to scale, but hopefully I can be forgiven for that. And so this is the tensor that we're working with. These three numbers, they are in 32-bit precision, and I want to quantize them. And so I have this quantize function here, and it takes as input a tensor, which is our tensor here, and a target data type that we want to represent our tensor as. And so for 8-bit precision, I'm going to first check if it's 8-bit precision, that's either signed int 8 or unsigned int 8. And if so, all this really does is check to make sure that it's int 8. If it's int 8, then we have to use the info method to get the minimum and maximum of that data type. If it's anything other than int 8, like 16 or 32, then we have to use the finfo attribute or method. Sorry, that's all that really says, and that's going to give us our qmin and our qmax that we got in our equation. And then we have to find rmin and rmax. Well, rmin is just the minimum of our tensor, which is going to be the -500 here. The Rmax is just going to be the maximum, which is going to be 300 here. And then you remember the scale formula, we just translated it directly to code. And then the 0-point formula is exactly what we did in our handwritten example. And here, the quantized tensor is just our regular tensor divided by the scale, and then we add back the 0 point. And then we are casting that once we scale it down. So here we've scaled down every single value. We've quantized every single value in the array. So they're now different values. They're different numbers. -500 will be -128. 300 would be 127, and then 100 would be like 63. And but they're still represented as 32-bit numbers. And so in order for us to get that memory savings, we have to cast them to int 8. And so we're going to use the to method, the .to method in PyTorch to cast it to 8-bit precision. And we're going to return all that so that we can print out and we have that information. So I'm going to pass in our tensor, I'm going to pass in our target data type to be signed int 8. And then I'm going to run this. And as you can see, this is our quantized tensor. -500 got quantized into -128. 100 got quantized into 63, and then 300 got quantized into 127. And as you can see, the minimum and the maximum values in this tensor do map down to the minimum and maximum values of the quantization range. 8-bit precision can assign to 8-bit precision the most minimum number, the lowest number it can represent is -128, and the maximum number it can represent is 127. And the min and max in our original tensor, our 32-bit tensor, map down to those two numbers. And as you remember, that was crucial in actually deriving the scale and 0 point in our quantization formula. And now I want to show you how that they actually maintain relative distance, right? That the relative distance between any two numbers in our original tensor is the same as, it should be approximately the same as the relative distance between the numbers in the quantized array tensor. And so I'm going to choose the numbers that are at index 0 and index 1 and compare the relative distances between them. That's going to be -500 and 100 in our original tensor, 32-bit, and -128 and 63 in our quantized tensor. So here we're going to get their relative distance. We're going to access them from the tensor, and we're going to subtract them off and get their absolute distance. Here we're going to get the range of the tensor itself, like what's the minimum, the difference between the maximum and minimum number, and then we calculate relative distance. And we're going to do the same thing for the quantized tensor. You will note here that I'm casting all of these numbers into float 32 precision, and that is because we don't have hardware in our Colab environment, and I don't have it to actually handle integer arithmetic. So we can't just subtract these two numbers as they are because they are in signed int 8 data type, and our hardware doesn't support that. We must have 16-bit or higher in order to be able to directly to subtract two numbers. And so we're going to get the again, the relative distance between the two in the unquantized range, in the unquantized value set, or unquantized tensor, sorry, and then the quantized tensor. And we're going to see what percentage of those, what distance, the distance between those two, what percentage it takes up of the range. As we explained in our intuitive explanation of linear quantization, as you can see, these values right here, the distance between -500 and 100, take up 75% of their full range of the values between -500 and 300, and the values their unquantized values here take up 74.9% of the total range here. So they're not the same, as you can see, and because they're not the same, that is our quantization error. Again, we want to repeat, linear quantization is the algorithm itself is as good as it is able to maintain the relative distance between two values in a tensor. And so if these two values, if their distance as a percentage of the range is exactly equal to their distance here as a percentage of the range in the quantized tensor, then if they're exactly equal, then it's perfect. If they're off, then that means it's imperfect, and most of the times that is the case, but our job is to minimize that relative distance. We want them to be as similar in terms of relative distance as possible. And so that's quantizing it, right? So we quantize this tensor down into 8-bit precision, and this is the tensor we got. How do we dequantize? Well, it's literally just taking the scale, and then what we're going to do is we're going to take the quantized tensor, we're going to subtract off the 0 point, and then multiply it by the scale. And if you remember that in our equation that I showed in the previous slide, that is how you get the original value back. This was actually the original equation that we used whenever we derived the scale on the 0 point. And so this is the equation that's going to get our quantized tensor back to our original tensor. And so when you run this, you get -500, 99.2157, and 300. So as you can see, they're now 32-bit because they have decimal places. These two numbers are the same, but this one's off. Well, that kind of makes sense because we noticed that our quantization error was about 0.10 here. And so this one's close, but it's not exactly 100. It was 100 in the original tensor before we quantized. And so once we quantized it, we got it down to 63. And then once we dequantized it, we got it back to 99.2157. So we lost some data there. And that is also how you measure quantization error. So that's two different ways. Two is measuring the relative distance between values. I think that's more intuitive because it gives you an understanding of linear, what the linear portion of linear quantization means. And here, this one right here, I think it's just easier to measure. And so that is how you quantize and dequantize a tensor. And so next we're going to kind of dive in really quickly to the quantization error, and I'm going to show you how to calculate it.